going to talk not exactly on the topic of the program, because I think there are a lot of talks related to what we did for almost periodic operators. So I would like to speak on something different today, and it's a classical topic. So actually it seemed to be closed for some time already. So with questions, but we had to reopen these questions and hopefully close them again. And the talk is based on a joint result with David Müller, who is currently a PhD student with us in Munich. And the publication is can be found in the archive, but sometime it should appear in the So what and I expect that every one of you knows the slides up to a certain degree. So at some point, maybe I will tell you something new, maybe however, at the very end. Okay, so I first wanted to reintroduce Dirac operators in 3 dimensions, and I'm not concerned much about constants, so I choose units so that most constants are ones. And then the free Dirac operator, which I denote by H naught, acts in L2 of R3 with values in C4, and is given by the, and I write it in the standard representation, minus I alpha times gradient plus beta, where alpha, this is a bold alpha, is it's a column of 3 matrices. Each of them has the structure 0, sigma k, 0, and beta is just the identity matrix on the first 2 components, and minus the identity in the last 2 components, and sigma k are Pauli matrices. So the natural domain on which this operator is also self-adjoint is H1 of R3, C4, but I guess every one of you knows it pretty well. So what I want to do, I want to first of all introduce a Dirac operator with Coulomb potential. So to the free Dirac operator, I would like to add something which I call V gamma of x, and at the moment it's just a scalar identity matrix times a function depending on x. It's just x to the minus 1, and the gamma is the coupling constant. So, and of course, if you're a physicist, then for you this potential describes the one which is coming from the atomic nucleus. So we think of an electron in such a nuclear field, and then if you think this way, then the gamma is in the physical units just alpha times z. So alpha is the fine structure constant, so in the standard units I use here, it's around 1 over 137. And z is the atomic number, so it's just for hydrogen it's 1, for helium it's 2, and so on. So it's the atomic charge measured in integer units. And well, so this is supposed to be a model for relativistic atom. Well, so if you look mathematically, so formally, of course, you can always add 2 operators to each other, H naught plus V gamma. But it turns out that in 3 dimensions, the singularity at 0 is strong enough to introduce some problems. Namely, only for gammas which are smaller than 1/2, it's you can understand this sum as an operator sum, because the second term will be relatively bounded with the bounds less than 1. So this is what hard inequality tells you. It corresponds only to some nuclear charges in nature. So you would think that everything up to order 1 in alpha z is possible, and you can find it in the periodic table. So you want as large gammas as possible, then it turns out that, well, you can just use the radial symmetry and the symmetries we have in this model and in each channel, well, you can separate channels in the total angular momentum and look at the Sturm-Liouville problem on the half line in each channel. Then the spectral analysis simplifies, and well, just by you find out that for gamma less or equals than square root 3/2, in every channel you are in the limit point case, which means that there is a unique self-adjoint extension of your operator which you can originally define on such a space. So if you exclude 0, of course, well, you can apply both terms to functions like this without leaving L2. And then, well, so for such gammas, the self-adjoint extension is really unique. Then, well, still you are not far enough in gamma, so you can ask for more. And if gamma is less than 1, then you still can indicate a unique self-adjoint realization of your operator, although in principle the deficiency indices are no longer 0, so you should select somehow. And the natural physical property which defines which realization is correct, it's said to be the one whose domain, so the domain of the corresponding self-adjoint operator is contained in H1 half of R3C4, which is the energy norm. So it is just the form domain of your original operator.
It is form domain, so the form is well defined?
Yes, the form is always well defined, but you know that in this case, also the operator domain is contained in the original unperturbed form domain. And this specifies you a unique self-adjoint extension. All other self-adjoint extensions are nice, but they don't have this property. Well,
why this property is important? H1 half.
H1 half. Well, well, if you're a physicist, you can see that the expected values of both terms exist separately. So you can speak of so for any state in the operator domain, you can speak of the kinetic energy and of the potential energy. So you just take the expectation value, expected value of this state. Otherwise, you will have to, you cannot decouple them. You can speak of the total energy, but not of kinetic and potential energy separately, because there are some constellations due to which your operator remains self-adjoint. Strange domains.
So just to clarify, so you say for gamma up to 1, there are many self-adjoint extensions.
Yes,
just
for all gammas bigger
you can
than
have a distinguished
exactly.
one.
For all
satisfying
gammas
that
bigger than
property.
this, the operator is not essentially self-adjoint. You have many extensions, and there is only one which satisfies that the domain is.
And what is this dimension of the space of extensions?
It grows, so you have many channels, right? So you can have a family of Sturm-Liouville problems. So for this value, the first one becomes a limit circle. But as you increase gamma, you have more and more channels which achieve this state. And then, so you on every step you have to define freedom increases.
So if gamma is less than 1, it's just one parametric family of extensions.
There are more channels.
There are more all.
Is it finite, just sort of stepping up?
Yes, yes.
Approaching
It's always
infinity as you approach 1.
Yes, the deficiency indices are always finite. More than this, actually, Esteban and Loss in 2007, they have, well, they introduced a philosophy of alternative to this H1 half condition. Actually, this H1 half condition is also not the only one you can use to select self-adjoint extensions. So there are others, but actually physically all of them lead to one certain self-adjoint realization. But then for gamma equal to 1, so Esteban and Loss, they actually have introduced a generalized Hardy inequality, which looks more complicated than the usual Hardy inequality. Still, it holds for all these cases, And then they argued that, well, if it holds for all gammas less than 1, let's just require that it holds also for gamma equal 1, and prove that again, under this condition, then you have, for gamma equal to 1, you already have infinitely many infinite diffusion indices, but still there is only single self-adjoint realization which satisfies this generalized Hart inequality. Actually, you can go past gamma equal to 1, so actually you can take any gamma you like, also bigger than 1, but then somehow there is no understanding as yet what is the natural distinguished extension. So there are many. They all, if you look at how they behave near 0, then they oscillate wildly, and everyone in a different way. So by now there is no understanding what the natural self-adjoint realization is, but I just wanted to say that there are many, and they are all self-adjoint. And actually, from the mathematical point of view, well, it's a question of choice. It's not a question that something fundamentally goes wrong. Okay, so, and all the self-adjoint realizations I have mentioned by now, they are just extensions of the symmetric operator which you get if you define the whole thing on C0 infinity, without 0.
0 stands for compact support.
Yes, 0, this 0 is for the compact support, and this 0 is the origin.
That's 0.
Okay. So now it turns out that for all these operators I have discussed, the essential spectrum is the same. It consists of two components. One is the negative half-line starting from -1, and the other one is the positive half-line starting from 1. And actually you can also see that, well, since it's the union of Sturm-Liouville spectra, well, you see that the nature of the spectrum, often you can prove that there is continuity, but there are also eigenvalues in the gap -1, 1. So which are, since the essential spectrum is this, they must be all of finite multiplicity, and you can actually find the corresponding eigenfunctions and realize that the values of these eigenvalues are given by a nice formula.
Where is J?
K here is equal to J plus 1/2.
Fantastic.
J is the angular total angular momentum, right?
But I don't know what notations you use.
Sorry. This J. Sorry, it should be K. Well, anyway, J is the physical index, which is just the angular momentum. So, but for K equal to J2 plus 1/2, you get an integer number. So that's why I actually have written K on the right hand side. Looks nice. Because otherwise you would have to look at half integers. Well, in any case, I just wanted to say that you know explicitly what the eigenvalues are. You know that they accumulate only at +1, and actually the first eigenvalue given by this formula approaches 0 as gamma approaches 1.
The first one is going to be...
The first one is going to be for n equal to 1 and k equal to n. So actually k equal to -1. Well, actually,
Eigenvalue depends on the modulus of K.
yes. But the k cannot take value n, but it can take value -n. This is just how it is. Well, it has to do with degeneracy.
Mm-hmm.
We should count them properly.
Dirac knew this.
I guess, well, I don't remember actually who have calculated this, but it was known in the 1920s.
I think he solved.
Yes, I guess he solved it first. But was he the first who derived?
Well, he derived the Dirac equation, and I think he solved. I mean, at least he predicted antiparticles.
Yes, but not for atoms, right? And not to predict antiparticles, you need to solve the free Dirac equation. You don't need.
Yeah, that's true.
potential.
But okay, maybe. So that's my question.
So
you don't know if he
I
solved
don't-
this. This would be
yes,
the
exactly.
first exercise that anybody would do, right?
Yes, I
Then-
mean, but the whole point of this thing is that when physicists solve the one-particle Dirac equation explicitly and they found the eigenfunction eigenvalues, they were very much excited because they got extremely nice approximations to the numeric values they knew from measuring the spectra.
Yeah.
And they, up till now, they believe that all the relativistic effects for the hydrogen atom are already taken into account here. You will have to introduce a lot of corrections due to quantum electrodynamics, different spin in spin orbital interactions are not counted for here. But as for the oops, sorry about this.
You should answer the call. Might be important.
Anyway, so I wanted to say that these eigenvalues are believed to be correct with some enormous precision. And this is what motivated people to work with Dirac operator, but of course it's complicated if you have more than one particle.
The spin orbit coupling is already in there, isn't it?
Well, I mean the electron spins are here. Maybe I should disable
Maybe you should switch the Skype off.
well, I can switch my wireless. This will guarantee that nobody can achieve. Okay. So this now let us perturb the system a little bit. Suppose you have added a perturbation with, say, bounded potential with decays and infinity. So then, of course, all the picture remains the same. So there's no questions about self-adjointness, essential spectrum. They all stay as we have discussed. But the eigenvalues can no longer be found explicitly. So then you would still like to find a formula which describes this eigenvalue and in some efficient way. Well, for bounded below operators, bounded above, it's a current minimax principle which does the job. So you want to generalize a current minimax principle to the operators with gaps in the essential spectra. And then, well, the most obvious formula would be, of course, something like this. You take the spectral projection of your operator corresponding to the negative spectrum, and it should be plus one here. No, sorry. It's correct as written. So it's a spectral projection to the interval -1 infinity, and then you just write the usual current minimax principle. So you take a vector subspace of finite dimension being k, and you maximize the quadratic form of your operator over this subspace, and then the minimax value, well, they adjust the current minimax value for the projected version of your operator. Everything is done. But of course, it's pure cheating, because you usually to find what this spectral projection is a harder problem than to find the eigenvalues. So this could work, but only in a very weak theoretical sense. So now let me introduce a class of potentials I would like to.
Otherwise, it is correct. That's what you're saying.
Well, I mean, it's definitely correct.
Because this is the perturbed operator already.
Yes, it's because the projection you take is already for the perturbed.
This is.
So, also, I mean, no trick.
Yes.
So, but well, I'm going to correct it. I mean, it's not an interesting result now. So let me just introduce a class of vector matrix functions V on R3, and these are those who satisfy this pointwise bound. So they are less or equal than 0, and they are bounded below by our 1 over x potential with some coupling constant nu tilde. And I just want to distinguish the classes where nu tilde can reach the value nu or not. So where nu tilde is in the open from the right interval 0 nu, I denote the corresponding classes of potentials p nu. And if nu tilde can achieve nu, then I just say that we are in the closure of P. Okay, so now we have an efficient parameter nu, which controls how strong the singularity is. And so it's just for later. So now, of course, physicists and chemics they tried a lot of different approaches to write still some minimax principles. Some of them look strange to us. Some of them turned out to be correct. And one of the correct one was introduced by Thalmann in 1986, and then Tolman, apparently, and Data and Divaya in 1988, completely independently. It's hard to suppose that they knew about each other. But anyway, so the formal proposal was to characterize the smallest eigenvalue in the gap in the following way. You split every 4 spinor you're looking at into 2 components. So if you look at a B spinor consists of 2 spinors phi and psi, and you just say T plus projects to the upper component, T minus to the lower component. And then you maximize over the lower components and minimize over the upper components. So this is the procedure as proposed. So, and for some mysterious reason, they write that it should somehow either approach or be exactly the first eigenvalue in the gap. Well, which looks surprising, because you somehow do not, you have the projections, upper and lower, right? And then, they are not the spectral projections of it, right? Not of the Dirac operator. But still the hope was that such minimax values give you the correct ground state energy for some mysterious reason. And
can you just remind me what the interpretation, the physical interpretation of the upper and the lower is? This particle and antiparticle?
So if you look at the Dirac operator, especially for large energies, then you realize that all the positive functions from the positive spectral subspace have strongly dominating upper components. And all the particles from negative spectral subspace are almost located at the lower components. So at least for high energies, you know that, this should be electrons and this should be positrons. And then if you're a physicist, you say, okay, it's approximate, but let's call these upper components electronic and the lower components positronic parts of your particle. And then what you do, you maximize over the electronic components, because this is what corresponds to the positive energies, and you minimize over, you maximize over positronic things, and you minimize over the electronic guys, and then you get the lowest eigenvalue. So for given
so that's the physical intuition, right, behind
exactly.
this. Yeah.
So given the upper components, you just play with the lower components to get the maximal energy, but then you minimize them. This is how. And then there was then the mathematicians come into the field, and first were Esteban and Serre, two French mathematicians who in 1997 replaced these projections T plus minus here by the spectral projections of the unperturbed Dirac operator. So, this intuition about what you call electrons and positrons, you can think of upper and lower components, but you can also think about being in the positive or negative spectral subspace of the unperturbed operator. So then you replace the projections by those two, and they announced that for V being a P1/2, so the coupling constant less than 1/2, the kth eigenvalue in the gap is characterized by the following minimax principle. So you take, first of all, suprema over all points, so you fix a subspace V of dimension k in the positive spectral subspace of the free operator. Then you add to this subspace all possible vectors from the negative spectral subspace intersected with H1/2 for obvious reasons. You want to stay in the Von domain. And then, you minimize over all possible choices of V. Actually, in this article, the result was announced, but the proof was promised in a later publication. H naught and V are the quadratic forms of H naught and V respectively. So you do the same thing as physicists did, but now you say in which spaces you work, you replace the projections, and it was claimed that the results are correct. So then there was a brief period of time when the proofs came. The brief history of rigorous result on minimax principles. So a general result, well, first of all, was introduced by Griezmer and Tintop in 1999. They studied they studied with bounded operators and looked at this kind of minimax principles for them. And then, however, they found an interpretation which allows bounded perturbations for Dirac operators. Namely, they found that the variational characterization of the lowest eigenvalue by Talman, Data, and Dwyer, the one with upper and lower spinors, actually is correct. So this physical intuition can be justified for potentials which are bounded below by a constant negative, provided they decay at infinity. Okay. Then in the same year, together with Lewis, they published an article where they proved that the approach of Esteban and Serre, the one with three the spectral projections of the Untitled Dirac operator, holds for V's up to the coupling constant, which is, well, about 0.3, and exactly the positive root of this equation. Okay, so then in 2000, Dolbeau, Esteban, and Serre, so they proved and extended the original result of Esteban and Serre to the class of V, which under an extra assumption of slow decay, well, contains P to with this famous constant. This famous constant is just the critical constant for the Brown-Ravenhall operator, for those who know what I'm speaking about. Anyway, in 2000, the question seemed to be closed because the same authors, Dolbeau, Esteban, and Serre, published an article where they proved the validity of both their and Tolman Data Dwyer approach for V's in P1. So up to the critical value 1, past which, in any case, nobody knows. Right? And then, of course, it was a famous result. It's hard to read, but I mean, even for mathematicians, it takes some effort. But it was famous in the sense that it got something like 70 references or more. And then, however, at some point we have looked with David at it again because we wanted to build upon it. So we were looking at some questions about Dirac operators, and then realized that there is a problem in what they did. And the problem was the following. So actually, they didn't prove the original formula, which I have copied here, but they replaced actually the positive and negative spectral projection projected H1 half by P plus minus C0 infinity, which is kind of nice because he is a very nice space. And for the Tolman version, it was replaced by the C0 infinity with a different projection. And their argument, actually at the very beginning, they require that C0 infinity of R334 is an operator core for 8. And then, working on this operator core, they get the whole result. It's a very non-trivial proof. But actually, well, and it's correct, but for Dirac operators, it's not applicable to the constants they claim. The problem is that the statement that you have an operator core for such a space is only holds only for the coupling constants up to square root 3/2. If you remember, I said that the operator is essentially self-adjoint up to this coupling constant, right? So then, of course, you have an operator 4. If, however, it's not essentially self-adjoint, then you have some freedom, and it means that it's not enough to know about what happens to operator on C0 infinity. So C0 infinity cannot be an operator. And then we contacted the authors of the original publication, and the answer was that they are aware of the problem with the proof, and they know that actually this is what really holds, but they were working on the correction, but not as far as to provide one. Then we have looked at it and actually proved the minimax principle of exactly as stated, and also for Tolman projections as well, in its original form. So without replacing h1 half by C0 infinity without origin. And our proofs are actually using the ideas which Dolbo, Esteban, and Serré applied in 2002, and Grissom and Zidetov in 1929. So it turned out that both approaches are important, but we need some extra input. In particular, we had to work consistently with quadratic forms instead of operators. And we had to introduce a lot of new objects and spaces in order to make the argument rigorous. So how does the result look explicitly? The formulation, so first of all, it's strongly adapted to the way how you construct the self-adjoint extensions for Dirac operators with Coulomb potentials. Namely, so let Q, let me go abstract a little bit. So Q be a self-adjoint operator in a separable Hilbert space H, and Q is its linear form. So then Nancy, in his article of 1976, introduced the concept of form perturbation of Q. Well, it's certain conditions should be satisfied, and if they are satisfied, then there exists a unique self-adjoint operator B, which you can interpret as the one corresponding to the formal sum of the quadratic form of Q and the quadratic form of V, with the following two properties. First of all, for every x from the form domain of Q, the supremum over y's of this ratio is finite, which basically means that, well, something is a bounded operator in the usual Hilbert space. Right? And it should hold for every x in D of Q. And of course, well, the quadratic form of the operator is the one which is just the sum of the quadratic forms of your original object for all x's which are in the domain and y's in the form domain of Q. Maybe later I can explain to you how what a form perturbation is. Basically, what you do is just you consider the whole thing is that there is no assumption about boundedness below or above for your quadratic form. This is where you have to work. So what you do, you basically look at the quadratic form of the modulus of your operator. Then you also shift it up with some certain constant, and then you get a Hilbert space, which is embeddable in the original Hilbert space, and you start looking at the perturbation in this Hilbert space. And then if it turns out that the perturbation there in this new Hilbert space is bounded and has certain properties, then you can return and, well, first introduce B in this other Hilbert space, and then well, what you get are these two properties 4 and 5. And so let two symmetric sesquilinear forms Q and B, so that the form domain of Q is contained in the one for B, and the self-adjoint operator B in a separable Hilbert space H satisfy these two conditions 4 and 5. Actually, we will not need more than these two formulae. So you can think of operators constructed as form perturbations of something. So then this argument about what Nancy did applies. Or you can just think that, well, you have two quadratic forms and an operator B with these two properties. So it corresponds to the form sum of the original objects. So now let us split our total Hilbert space into orthogonal sum of two components, and let lambda plus and minus be orthogonal projections onto H plus and H minus. So now the main abstract result I would like to present is the following. So we make three assumptions. First of all, if you act with your projectors to the form domain of Q, then you stay inside the form domain. So the projections do not spoil anything on the level of the unperturbed quadratic form. The second assumption is that if you take the supremum over all points from the negatively projected things, so D minus is a negatively spectrally projected, well, projected with lambda minus version of D of Q. Right? And then you take the supremum over all axes there of the sum of the quadratic forms, and you want it to be finite. Which basically means that you have some certain implicit control over how much your projector lambda minus differs from the spectral projection for the total thing. Right? But it's on the level of energies. So you can hope that things like this holds true, and in part for say if V has a sign, then say the negative spectral projection of Q is always all right. So then you introduce the minimax values as before. So you take, well, first suprema over V plus D minus, and infima over V in D plus, with dimensions of V equal to K. So this is the same thing as we do all the time. And call these minimax values lambda K. The essential assumption is that the first one should be strictly bigger than this supremum over here. So this condition is also implicit, and it's actually much harder to verify than all the others. This condition shows up already in the work of Tolstoy. And then if you can prove all the three things, you just introduce B as an infimum of the essential spectrum intersected with A infinity. So A is a natural bound from which on you can say something about the spectrum. So, and if you look at the spectrum to the right of A, then it turns out that the kth eigenvalue of B in the interval between this value A and this value B, which is basically the beginning of the essential spectrum to the right of A. So in this spectral gap, you restore all the eigenvalues of B by taking the minimax values. And if there is no kth eigenvalue, then our minimax values just stabilize at the level. So it's just like the current minimax principle, but now it works in the interval between this A and this. And we can apply this result to the Dirac operators, namely, so if you have a Hermitian 4x4 matrix vector function V, which satisfies this condition, I haven't corrected it, sorry about this. Actually, I wanted to write the class P1, so the inequality here should be strict, and instead of mu tilde, you can just write 1. No, sorry, you can write anything less than 1 as nu tilde. This is the correct statement. Yes. So you take nu tilde, which is strictly in the interval 0, 1. If your V of x satisfies this pointwise bound, it is of course measurable. Then both for the free spectral projections of the unperturbed, for the spectral projections of the unperturbed operator P plus minus, and for the projections onto the upper and lower components, the minimax values lambda k, computed in the usual way, coincide with the eigenvalues in the gap minus 1, 1 of the self-adjoint realization of H, which is equal to H naught plus V, with the domain contained in H1 half R34. You actually see why this condition is natural. So exactly for the physical self-adjoint realizations, we can provide a formula which is analogous to word minimax principle. And as said, actually everything I did is nothing new, but the corrected version of a very lively discussion which took place in the, from 1997 to 2000, and then it was considered that the ultimate solution is obtained. But now, well, it turned out that it was not so, and now we can claim that it's obtained again. Right, so maybe a couple of remarks. So here, the whole work goes into proving this condition number 1 is bigger A. Well, I mean, both, well, this is implicit, and for this reason, I didn't call this object corollary, but I call it the theorem. Because to prove that even for Dirac operators it holds, it requires something. And what it requires is to, well, look here. If you have some certain choice of V, so the positive component is fixed, you should in a clever way be able to choose a corresponding X, so that the energy is bigger than if you just take the supremum for V not being here, right? So you should show that any choice of something belonging to D plus actually pushes the energy up. And sometimes you can do it explicitly, sometimes you resort to indirect reasoning, but this is how you... Also, if you start proving this theorem, it turns out that one inequality here, so this equality is two inequalities, so one inequality is pretty easy. So you can very easily argue that lambda k's are less or equal than mu k's. Well, and this is where we use the argument of Grisman-Siedentop. So basically what you do, you can, if you know that there is some eigenvector to lambda k, then you just start well, seeing that if you shift your eigenvector in the negative part, you can well, you can always attain a value which is almost lambda k. So this part is easy. So the hardest part, well, I mean, we really follow the proof of Dolboy's dependence array, but we had to introduce some extra structures in order to do it properly. But there's a benefit, we no longer speak of any operator domains at all. But I don't think I want to go into the details of the proof because we tried to recover some structure, but the structure consists of many steps of equal values. So I will not go into it. So unless there are questions.
Thank you very much.
So the Tolman result actually extends to all eigenvalues,
Well, to all coupling constants up to 1.
but also to more than the ground state. As you stated.
Yes. So this was claimed already by those authors. So then, let me see. Yes. So already Grisman-Siedentop said that Tolman the divider holds under certain conditions and for all eigenvalues. So it was written originally for lambda 1, and this is why, well, if you read Tolman and those two authors, that they only speak about the first eigenvalue. So they didn't make any statement about lambda k.
Okay.
But the generalization to lambda k is pretty straightforward if you know who. And then, so all the authors in this story, they try to prove the formula for lambda k also in the Tolman case.
Are there known atoms with gamma bigger than 1?
Well, there are, so the physical value of alpha is 1 over 137. So gamma is alpha times the atomic number, and there are by now no really atoms about 120, right? So that's pretty much room. And all those who are proven to be existing, right? I mean, well, everything heavier than iron is unstable. So then those guys whose alphas are above 100, they exist, but for certain times. And for alpha equal 117 or something, they exist, but the times are so tiny that, well, I mean, this, it was always a discussion whether you call them just resonances or real nuclei. So you basically see that you let something collide, that the track is very short, non-zero length, and then everything.
So it could be that there is
Splits.
nothing for gamma bigger than 1.
Right, so there is also a concern by physicists, right? So the physicists, they knew that something goes wrong with their solutions for gamma bigger than 1. In particular, if you look at the ground state, the lowest eigenvalue, then actually the graph of it after all the simplifications, this formula, as I told you, n is equal k, equal 1, n is equal modulus k equal 1, then the graph for lambda 1, so this is the energy, this is gamma, is a perfect circle of unit radius. So the energy equal 1 is the beginning of the essential spectrum. This is the constant level. So here everything is covered with the spectrum. And the first eigenvalue, it just goes in a perfect circle to the point equal to 1 equal to 0. And then past 1, it kind of disappears. If you regularize your potential, then it does something like this. And then as the regularization parameter goes to 0, it just starts disappearing. And what physicists...
What is that? What is this? What you did now? What is this level?
This one?
No, I mean, you draw a horizontal line.
So this is -1. This is where the second component of the essential spectrum begins.
Mhm.
So so my gap is always between these two levels. And all the eigenvalues are here, so you have the first, the second, the third, and so on. So they behave in such a way. So for any, you have a non. So the bigger is set, the bigger distance you go into. But if you remember, this one, it's actually physically mc squared for the electron. So if you are speaking of energies of order 1, you are speaking of energies of order mc squared. What it means? It means you can produce an electron-positron pair. So 2mc squared is the price to make a couple of electron and positron out of nothing, out of vacuum. Right? So now you are speaking of energies which are at least half able to do the job. So it means that the contributions from vacuum polarization, as physicists told us from the work of Dirac on. So they are not negligible. So your model, which describes an electron in some external field, actually for energies of this size should not be consistent in the sense that you cannot speak of one single particle. So you should extend your space to allow more particles, just being produced due to the interaction of your original particle and the external field. So basically your external field is so strong that it starts producing particles out of nothing. And then they say, look, our model is actually not applicable for these values of gamma anyway, because we know that we need some corrections due to this vacuum, this particle generation. And so mathematically it's all very interesting, but if you speak to physicists, I think this will be the answer. So you leave the area where your original assumptions are satisfied.
But mathematically we can still continue talking, right?
Yes, we can.
So,
Well, I mean,
what can you say about gamma greater than 1, mathematically?
This is what we are looking at with a colleague in Munich, actually. And strange things happen. So, first of all, well, I mean, the most fundamental question is to specify the self-adjoint realization you are looking at. The second question is, suppose you have chosen a nice self-adjoint realization, or at least your favorite self-adjoint realization for a certain value of gamma. So all of the self-adjoint realizations, they are described by an angle between two solutions for the Sturm-Liouville problem, right? So you have one or several angles like this, and suppose you have made some agreement which angles you choose for given gamma. The question is, if you start moving gamma, should you keep the angles the same? What makes you keep them this way? And because well, for every gamma you have several solutions which behave in a different way, so the mixing angles among them is also kind of arbitrary thing. It depends on which solutions you take, right? And then, well, so this is exactly the question. Find a physical principle which allows you to say, I should look at this solution and not the other one. As soon as you fix something, you can start studying their spectra. And it turns out that there are, for example, ones, apparently, which actually fit in with all the limiting values of the eigenvalues you got before. Certain choices of your self-adjoint extensions. But since we don't know how whether we should keep our extension parameters or not, we cannot discuss what happens to them further on, right? And the most challenging thing is to realize what happens to this one, right? It kind of was here, and then it disappeared, so you cannot continue it.
Is it in the complex plane? If you look at the formula, it goes in the complex plane.
Exactly. So what?
This is our question to you. Yes.
Well, so it's an interesting question. So we have, well, we still didn't give up to understand what may be said. But the first question would be to realize whether there is a natural self-adjoint extension.
That would be a non-self-adjoint extension, right? That you're looking for now.
Well, I don't
Where
know.
the formula still holds. Where the formula still holds.
There is some, I don't remember the reference, but there is some paper, I mean, in the mathematical, Journal of Mathematical Physics or something like that, a very old one, in the 80s, well, very old, relatively old, where they consider extensions to gamma greater than 1.
Mm-hmm.
Do you remember what I'm talking about?
No, I'm not sure.
And they have, I don't remember that, but I remember that they kind of look at analytic continuation and then they...
Well, actually, there is a group of people who look at these questions, but I think it was not something. So what I know, they didn't look at the analytic continuations.
Right.
They just applied the general Sturm-Liouville theory to gammas bigger than 1.
Mm-hmm.
Well, since no problem. So we just have a lot of different extensions, and then they ask questions which, to me, were not the most interesting ones, but it's personal choice and what you consider interesting. But no. So they, for example, ask, given a value, say -1, for which angles of my self-adjoint extension I have an eigenvalue exactly there.
So you calculated what you formally get with the minimax formula for gamma bigger than 1.
Well, you have to specify the potential, right? Pure Coulomb potential.
Yes.
So, I must admit we didn't try. And
Because the
actually,
question is if that would extend these
and-
curves somehow.
well, then you make an implicit assumption that the minimax principle is applicable. Right?
Yes, but I
Yeah,
mean,
sure.
but you could say you could formulate the question the other way and say, okay,
Now we're looking
let's
for
see
the
what we get
extension.
with the minimax principle, and now which extension satisfies these eigenvalues.
Yeah.
Well, this is, well,
And let's call it an
well, it sounds interesting. Right.
But
I don't know
formally you should.
what will come out. The problem is that actually the conditions in the minimax principle, right, are such that you basically require that your subspaces you are choosing, or so the positive and the negative, lambda plus and lambda minus two projections, they're not too far away from the real spectral projections, right? And then, so the bigger perturbation you make, the less are the chances that, well, the angles among them will not grow too big so that everything collapses. And this is this was the reason why there were different proofs for minimax principle. Actually, I made one in my master's thesis, so which extended the result of prism and hidden top to bigger values of the coupling constant. And it was considered substantial, but then it turned out that it's so the French result was just more general. So although our original assumptions were formulated differently, under which the abstract results are. Still, I mean, it's not expected that formulae work for all possible lambda plus and lambda minus in the world. Right? I mean, that's by far not reasonable. I mean, if you take just the spectral projection of your full operator, but to a different interval, right, which is the wrong one, definitely you will not get the eigenvalues. Right? It's not to expect. So,
Any more questions? Thanks again.